I'm Bob Paxton with Allied Edison. A ground fault has just occurred on your station's DC ungrounded system. You know that you're now operating with a compromised system. You also know that you need to try to find it before a second ground fault comes in. But what do? Should you open breakers, even though there may be unplanned consequences to de-energizing circuits? Perhaps you would decide to take apart junction boxes to perform continuity or mega readings, all the while knowing this could take days or even weeks to find the source of the ground. Or would you prefer to use state-of-the-art equipment that is so unique it can trace the source of the ground fault without de-energizing the circuit? Equipment so profound it can provide accurate data about the ground fault conditions in assessing risk. Equipment that is easy to operate, it can quickly identify the source of the ground fault. Equipment that can see through a conduit or a flex, bundle of cables. Equipment that is so incredible it can log data and locate all types of grounds, including intermittent grounds, even in a sea of capacitance. Well, I invite you to join in and watch a field demonstration of that very type of equipment, the Allied Edison ZX3 DC ground fault detection and location system. In this video, a sustained DC ground fault alarm has just occurred in a nuclear power plant's control room. 2 technicians have been dispatched to the source of the alarm at the station's cooling towers. Let's have a look at how they locate this ground fault, shall we?
Alright, we're at a DC D panel, and there's been reports of a ground. Obviously, we see our ground detector alarm has come in. We're going to verify off of the bus, which is the voltmeter. We're going to see what voltage we're seeing to back up the light. Yeah, positive to ground of 125. Negative to ground is about 10 volts. It's a pretty reasonable ground, and it's going to be on the negative side.
Is that form cover?
Yeah. We cover. This is the ground detector itself. The ground detector has a reference to ground, so the ZX3 will find it if it tries to find the ground. So the first thing we have to do is disable the ground device, and we'll do that on an electromechanical by pulling the brush. Now that we've done that, you can see our ground resets, and now we can check the voltage off of the voltmeter again and see how the ground has changed characteristics now that that reference to ground has been removed. So again, starting from positive to ground, now we see 134, and negative to ground is the remainder, 0.2. So we're still seeing evidence of a pretty good ground on the negative side. Alright, we've got our base unit hooked up. We've got positive to the positive side of the voltmeter, negative to the negative side, and we've got ground going off the stud in the frame for our ground reference. We're going to go ahead and turn the box on. Now we're going to go to detect. Alright, let's see here once. It's done thinking. We're seeing our full voltage, 134.7. We're seeing an open on the positive side, which is what we expected. We're seeing 700 ohms on the negative side. So a nice strong ground. Now we're going to take it to fast locate. Going to turn on the tracer unit. Take the mode select to fast locate. Now we're going to start dialing up the current adjustment. Right now we're seeing a fluctuate from about 3 to 5 milliamps, which is an acceptable scale. We don't really want to go over much over 5. Us enough signal that we will definitely be able to see this. Alright, so we've got the side panel off, giving us access to the leads coming off of the breakers, and we're going to go through and check. We'll clamp each one, pull our hands off it, and wait for it to settle out. So we don't see anything on this breaker, so now we're going to move on to the next. Again, no real response. We expect to see that rhythmic pulsing pretty much right off the bat. If you don't see that, it's generally a pretty safe bet to move on to the next one. So here, going off the third one from the bottom, we're seeing the same deflection we were just seeing on the calibration. So now we're going to check the rest of them while we're in here just to make sure we don't have multiple grounds. But we had it calibrated for getting up to about 19, and we just saw it hitting 19 there, so it doesn't seem like there's much stray leakage. All right? Again, we can see here that we don't get the rhythmic pulsing, and we still have the blue LEDs at the bottom telling us the tracer isn't detecting its own signal. Can you put it back on 30? So now going back to the one where we've seen it, we get the green LEDs indicating the box sees its own signal, and we're seeing the full rhythmic deflection of the LEDs. So this is telling us that 3 from the bottom, we see it. So for us, that means we're going to be going to load center 30 Bravo, 30 will be the next spot we go to.
Notice how easily the ZX3 was connected to the DC system. The red lead goes to the positive rail, the black lead goes to the negative rail, and the green lead goes to ground. These connections will always remain the same. By connecting the ZX3 to the DC main circuit panel, understanding the system data displayed, and then clamping individual branch circuits, these technicians were able to quickly identify which branch circuit contains the ground fault. Notice the battery bank and charger were immediately excluded as being the source of the ground fault by the ZX3 displayed calculations. By observing the panel schedule, the technicians know exactly where to go downstream from here. Let's continue to follow them as they clamp conduits and wire bundles on their quest to find the source of the ground fault.
So here we are in the back of L30. We know our control wires come across the bottom of this little trough. So we've clipped onto them at the first point we see, and we're seeing the indication we expect. So now from here, we're going to check the next cubicle over and try to figure out which column of breakers it's in. Alright, we can see here we have stopped seeing the indication we expect. Clipped into the second row of breakers, so that tells us that we're no longer between the base unit and the ground, so we're going to be in one of these three breakers here. So now we'll verify off of the fuse blocks and we'll see which breaker contains the ground, which breaker circuit contains the ground. Alright, so we can see we're on the DC control power fuse block for the bottom breaker. And we're seeing no indication. Now we are on for the middle breaker, and again, no indication. Finally, we are clipped onto the top fuse block for the top breaker, and we're seeing our indication. The signal strength is a little bit weaker, but we've also changed CT sizes. So at this point, if you really had to confirm it, you could go to your original box, but this is something we expect to see out in the field, your signal intensity changing depending on which CT you're using. So from here, the odds are it's either in the breaker or it's up on the cooling tower in a vibration switch, and 99% of the time we know it's up there, so we're not going to bother troubleshooting the breaker any further. We're going to go up to the cooling tower and go to the vibe switch and prove the circuit up there. Alright, so here we are at fan A03 Lima. And we know this is the conduit running up to our vibe switch here. So we're going to clamp as close to the vibe switch as we can, just to eliminate any extra cable that could potentially have the ground in it. And you can obviously see the rhythmic pulsing of the LEDs. We can see our 4 green LEDs telling us that indeed we do have a vibe switch with the ground.
Well, wouldn't you agree? That was simply amazing. And to locate the source of the ground fault took only about 3 hours. Did you know? Engineers estimate that a loss of a cooling tower fan at this station roughly equals half a megawatt loss of electrical generation, a cost that was easily avoided by the use of the ZX3 in locating the ground so quickly. In fact, just finding this one ground without having to open breakers, junction boxes, it most likely paid for the ZX3 itself. Consider this. Let's say that a ground fault does indeed compromise your DC system. You knowingly wouldn't operate with a compromised protective relay, would you? A relay intentionally designed to keep catastrophic events from occurring? So why would you ever continue to operate with a compromised DC system that feeds protective relays and controls? The answer, it seems, is obvious. Find the ground as quick as possible with the most reliable equipment. That's why I always say, and for you viewers out there, remember this: a station's protection, tripping, permissive circuits, breaker open and closed, status, controls, and indication circuits are only as good as the DC system that feeds them. Thank you for watching.